So we are ready with our second talk, and we are fortunate to have Dr. Monika Singh among us for this talk. So Dr. Singh will deliver her talk on quadrature, visualization, and computation. So Dr. Monika Singh, she is an associate professor at Department of Mathematics, Lady Shri College for Women, University of Delhi, and her research area include functional spaces and inequalities. So this is also noteworthy to mention here that Madam was an alumnus in PTMT like me. So I welcome Madam to this program. So now the screen is all yours. So please.
Yeah. So 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 thank you so much for a nice introduction, Dr. Uday. So before starting my talk, I would like to give thanks to the organizers of Curry Leave Days 2024 and making a PTMT Day 3rd edition a particular event of this program. Also, I would like to give thanks to Professor Satya for his continuous and encouragement for the PTMT participants. Because my talk is a part of the PTMT Day 2024 3rd edition, so my talk is more inclined towards the pedagogy of the content which I am going to present here. So the title of my talk is Quadrature, Visualization and Computation. In this talk, first I am going to discuss method of exhaustion, which is one of the method for computing quadrature and in particular area of circle given by Archimedes. And after that, I will depict that how the area of circle can be obtained or approximated by area of n-gon, and this idea can be generalized to find out the volume of a right circular cylinder by volume of a prism, right prism, with base n-gon. After that, I will discuss area of plane regions with curvilinear boundaries and what is the idea to compute that, idea of Riemann as well as idea of Darboux. And finally, if time permits, then I would like to discuss the question, how much discontinuity can an integrable function tolerate? So, what is quadrature? Computing the numerical value of the area of a plane geometric figure by dividing it into shapes of known area, usually area of polygons, and finding the limit as the divisions become finer. Now, one of the method for computing quadrature is method of exhaustion. This method is all about obtaining the area of a given circle by inscribing or circumscribing a succession of regular polygons inside or outside it and allowing the number of sides n of polygon to increase indefinitely. As n increases, the polygons tend to exhaust the region inside or outside the circle, and the areas of such inscribed slash circumscribed polygons become better and better approximations to the exact area of the circle. So whatever I have read about the method of exhaustion, let me explain this by using animation. So for animation, I'm using Mathematica and Mathematica software. And this animation I have made myself. So this is a circle of radius r. And here it is a regular polygon with 3 sides, which is equilateral triangle. Let's increase number of sides of this regular polygon. So now number of sides are 4, which is a square. Now number of sides are 5, that is pentagon, regular hexagon, polygon with 7 sides, regular polygon with 8 sides. And it's visible how the area of these regular polygons are exhausting the area of circle from inside. It is regular polygon of 16 sides, 17 sides, 18, 19, and 20, which is the maximum limit in Mathematica. So this, we can analyze that this is method of exhaustion, that from inside, how the area of polygon of 20 sides is going to exhaust the area of circle from inside. And it's also visible that this is the error. So let's see once again this animation. So this is the way how when the number of sides of these regular polygons are increasing, the area of regular polygons is exhausting the area of circle from inside. Let me show it by computation. So please allow me uh, so let me do computation and show that if we have a circle and inside this circle, if suppose I have made from inside this regular polygon, and this is pentagon, this is center. So what is area of n-gon, which is inscribing in this circle? So this is n into, why n into? Because this pentagon has divided this region into n congruent triangles. So when we are plotting n-gon, then this is equal to n into area of triangle ABC, because n congruent triangles. So here this angle is theta. So theta is equal to 2 pi by n, because there are n congruent triangle inside the region of inside this circle. So this is equal to n into, let me draw perpendicular from center to this chord, and this point is D. Again, these two triangles are congruent. So this is base, which is B by 2, and this is height. So area of triangle ABC is equal to half base into height. So this is equal to, what is base? Height is equal to, because this is radius r cos theta by 2. And what is b by 2? B by 2 is equal to r sine theta by 2. So n into, sorry, n into half into base. Base means 2r sine theta by 2 into h. H means r cos theta by 2. So this is equal to r square n by 2 into sine theta, because 2 sine theta by 2 cos theta by 2 is sine theta. Now multiply and divide by pi and putting value of theta. Theta means 2 pi by n, and this is also, it can be written as 2 pi by n. What is n here? Number of sides of regular polygon. So if number of sides of n-gon is increasing, that is n is approaching to infinity, it will approach to 1, and ultimately area of n-gon from inside is approaching to pi r square when n approaching to infinity. Now let's do this exercise for, now let's do this exercise from outside. From outside again, let's draw regular n-gon or circumscribing this circle from outside. This. Now this time, if this is center, please excuse me because I haven't made exactly regular polygon from outside. So this point is A, this B, and this C. And this is n-gon. So this time, area of n-gon circumscribing is equal to, again, n into half, base into height. This time, draw perpendicular from A to this point of contact. This time, height is equal to r, and this angle theta is again 2 pi by n. So this time, height is equal to r, and b by 2 is equal to r tan theta by 2, because this angle is theta by 2, and this is b by 2. So what is b? B is 2r tan theta by 2, and h is r. So this is equal to r square into n into tan theta by 2. Again, multiply and divide by pi. So this is equal to pi r square. Put value of theta by 2, which is pi by n. This is pi by n. As an increasing number of sides of regular polygon are increasing, it is approaching to 1. It means this is going towards pi r square. It means area of n-gon is approaching towards, these are circumscribing n-gons, is approaching towards pi r squared when n approaching to infinity. And from here we can say that area of circle is equal to, of radius r, is equal to pi r squared. Now let's see how this idea can be generalized for approximating volume of right circular cylinder by volume of prism. So here, this is prism with base n-gon, and here n is equal to 3. So equilateral triangle, top and base, both are equilateral triangle, and this is prism. Now let's increase number of sides. So this is prism with base and top square, that is number of sides are 4. So now pentagon, hexagon. So base is regular n-gon, 8 sides, 9 and 10. So in Mathematica, the number of sides, maximum sides of prism I can take only 10. So it is visible that how the area of right prism with base n-gon, sorry, not area, volume of right prism with base n-gon is approaching towards right circular cylinder. So in this way, we can approximate volume of right circular cylinder by volume of right prism with base n-gon. So this is the animation which I have made again myself. Yes. So now let me proceed further. So there is another perspective to compute again area of circle. Let's see how. As we all know that this time, let's plot this circle in this coordinate axis. And we know that this area of this circle can be computed. Area of circle can be computed 4 into area of this shaded region. Now, what is this shaded region? This shaded region, this is y is equal to fx, where, because equation of circle is this, center, origin, and radius r, so y is equal to under the root r square minus x square. So this area of the shaded region in general can be interpreted as area of region bounded by curve y is equal to fx, x is equal to a, x is equal to b, and x-axis. It means if we know how to compute area of, if we know how to compute area of region which is bounded by this, then we can easily compute area of circle. So our problem is to approximate area of this portion. So let me discuss idea of Riemann first. Riemann was German mathematician of 19th century. So what was his idea? Let's take finite number of points on this x-axis. And first of all, because I'm interested in area, so I am assuming for the time being that f is continuous on closed interval AB and f is greater than or equal to 0 because for the time being my objective is to approximate area. So what is first step? Our first step is to take few points on this interval AB. So suppose this is x1, this is x2, this is x3, this is x4. For symmetry, let me take x5 and this is x0. Now what we can do, we can take height, making rectangles of taking height is equal to f of x1. So this is rectangle with length x1 minus x0 and height f of x1. Let's take second piece. Again, what is height? Height is f of x2 of the second rectangle. And what is width? Width is x2 minus x1. Proceeding in this manner, we can approximate area of this region by sum of areas of these rectangles. It means, approximation of this region is equal to f of x1, area of first rectangle, area of second rectangle, area of third rectangle, plus 1, 2, 3, 4, 5. There are 5 rectangles, so x4 and this. So it will give us approximate area of this region, which is under the curve, y is equal to fx, and bounded by x is equal to a and x is equal to b and x-axis. Now the question is that why I have taken all the time height corresponding to right end point of this interval or of this piece. So here it is not a hard and fast rule that to take only right end point of this interval. What we can do, we can take any point. We can take any point x is equal to a, x is equal to b. We can take any point, and these points not necessarily be equidistant. And this time what I am doing, I am taking height. I am taking height is corresponding to midpoints of these pieces or these subintervals which I have made. So midpoint means this time height is this. So in this rectangle, what is width? Width is x1 minus x0 as the previous case, but height is f of t1. And here height is this. This time height is f of t2 and width is x0 minus x1. Similarly, here height is this, height is this, and height is. So now the area of approximation is, and so on. So area of approximation is, now I am writing in abbreviation, summation f of ti into width, length into breadth, xi minus 1, which is ith interval, and I varying from 1 up to 5. So this is called Riemann sum. Riemann sum, this is called Riemann sum, and here we have freedom. So here we have freedom to choose any of the point, can choose any of the point from these pieces. In the previous case, I took right end point, and in the second case, I took midpoint of each subinterval. So this is the way by which we can approximate area of region bounded by y is equal to fx, x is equal to a, x is equal to b, and x-axis. So let's see this with the help of animation. Let's see. Just a minute. Please allow me for stop sharing. I think it's just a minute. It's hanged. Shall I leave and join again, Dr. Uday?
Yeah, you can.
Okay. We are not able to see control also.
So your device is hanged or what?
Yeah, I think the laptop is hanged due to sharing of the screen.
Okay.
Let me do it again. Audible?
Yes, you are audible.
Okay. Actually, I'm not able to see leave button in my Zoom in laptop so that I can restart. Yeah, it's visible, but it's inside this. So now, am I audible?
Yes, and the screen is also visible.
Oh, thank you so much. Okay.
Yeah.
So now let me show the animation through Wolfram demonstrations project. So this is function log x plus 1. I think you just focus on the cursor. And here, as I did in the writing that I'm taking right end point, here interval is 1 to 0 to 5. And I have made 5 rectangles here. So actual area is 5.7506, but estimated area of these 5 rectangles is 6.793. So let's increase number of, and every time height has been taken corresponding to the right end point of the interval. So let's see how the how the number of points are increasing. How the number of points are increasing, and the estimated area of the region is approaching towards the actual area of the region which is bounded by curve y is equal to fx. So the number of, finally, this is 24 rectangles, and finally, the number of rectangles are increasing. And at the end, we have 66 rectangles. And you just see that estimated area is 5.180, but actual area is 5.7506. And if we take midpoint as I did in the same function, log 1 plus x, now I am taking height corresponding to midpoint of intervals. So you just see here height is corresponding to midpoint of this interval. So there are 4 rectangles. Actual area is same, but estimated area is 5.8005. So you just see as the number of points are increasing on x-axis, estimated area is approaching towards the actual area under the curve. So this is Riemann sum, animation of Riemann sum for function log x plus 1 over interval 0 to 5. So here you can see there are another examples also. Suppose here example is 1 minus x whole square. This is a function which is highlighted in blue color. And again, we are taking the pieces of this interval 1 to 0 to 5. And height we are taking corresponding to midpoint of each piece. Then again start, the actual area is 21.667, but estimated area is 21.0156, which is on the screen. So let's see animation. As the number of points are increasing, number of rectangles are increasing, and the estimated area is approaching towards the actual area of this region, which is bounded by function 1 minus x whole square. So this is Riemann sum, and this is the animation by which we can understand the process of Riemann sum. So now let me again move to the, so in this manner we can compute Riemann's by using Riemann idea and Riemann sum, we can approximate area under the region. Now, technically, when we do when we take pieces of this interval AB as x1, x2, x3, x4, x5, x6, and x0. So this is denoted by P, and these are points from interval AB. But what is the beauty of these points? That there is this relationship amongst these points. Always initial point is A and terminal point is B. So this is called partition of closed interval AB, which is, what is partition of AB? Which is a finite, ordered set. So, and this is denoted by SFP dot. This is called tagged partition. Tagged partition means we have this freedom. We have this freedom. These are pieces. And we have freedom to choose any point from this subinterval xi minus 1 xi. So I can choose xi star from anywhere. So this is the notation for Riemann sum. Because I am interested in area only, so I have assumed my function is greater than or equal to 0 and continuous. But actually, there is a guarantee because I'm assuming it is continuous. So what Riemann says that there exists R greater than 0. And in this particular case, this R is actual area. So as per Riemann definition, there exists R greater than 0 and for all epsilon greater than 0, there exists delta greater than 0 such that difference of this approximated area minus R. Let me repeat once again, my function is greater than or equal to 0 and continuous for the timing. That's why I'm saying approximated area minus R, which is actual area, is less than epsilon for all partitions, tagged partitions P naught, with there is one condition with maximum of these lengths is less than delta, where maximum has been taken over all subintervals, length of all subintervals, which we have corresponding to partition P. So this is definition by Riemann to compute area or approximate area by using Riemann sum. Now let's move to idea of Darboux. Darboux was French mathematician or 19th century French mathematician. And what idea he gave, because we are assuming that f is continuous on closed interval AB, f is continuous on closed interval AB, this I am assuming, and this implies f is bounded on closed interval AB. Because every continuous function on closed interval AB is bounded. It means if we take any partition of this interval, suppose this, then this function is bounded on each piece. On each piece. It means I can talk about supremum of f when x is in the interval xi minus 1 xi and infimum of this interval for every I, whatever the number of pieces we have taken, infimum of f of x is in the interval xi minus 1 xi. So now, what Darboux suggested that if this is x and this is y, this is coordinate axis, and we have this curve, y is equal to f of x is equal to a, and x is equal to b, and I have taken these pieces. So this time I have to take, this is x1, x2, x3, x4 pieces, this is x5, this is x0, width of this rectangle, again x1 minus x0, but height I have to take, height would be m1. What is m1? Supremum of this function f over this interval. So in this interval, this is supremum at this point. So this rectangle, it means area of this rectangle is this. For the second one, because in second one, it is an increasing function. So this time, this is m2, that is width is x2 minus x1 into m2. m2 is supremum of f over this interval x1, x2. And similarly, here, because this function is increasing, so supremum we will obtain at x3. So now x3 minus x2 into m3. m3 is supremum. And here, this. And here, this. Plus x4 minus x3 length into width into height, which is area of these rectangles. And finally, this is the approximation of this M5. So this is approximated area. This is approximated area. This is approximated. This is approximated area of this region. And because this approximation has been done from above, you just look at that all these rectangles are covering this region as the method of exhaustion from outside. So this is called upper Darboux sum. Upper means approximation of area from above. So that's why it is called upper. And sum means because it is sum of all these rectangles. So notation is U, F, P. Because U means upper, F means bounded by F, and P means corresponding to partition P. So what is upper Darboux sum? This is sum of areas of all these rectangles. Similarly, as we did in method of exhaustion, estimation from inside. Inside means, let's look at, inside means X and Y. Again, this is curve Y is equal to fx. Again, we have taken few points. Suppose this time I am taking only 3. This is A, this is B. So this time we are taking infimum height according to infimum. So this rectangle and here, this rectangle and finally this rectangle. So this we are approximating area from inside. So that's why this is called lower Darboux sum, and it is denoted by LFP corresponding to partition P, and this we have obtained infimum over interval xi minus 1, and this is length I varying from 1 up to. So if F is bounded on AB, or in particular continuous on AB, then we can always talk about LFP, and UFP means approximation from above and approximation from below. This is always greater than or equal to actual area, and this is always less than or equal to actual area. Now, because capital MI is always greater than or equal to small mi for every point, for every subinterval corresponding to partition P, and if we multiply this by length, both sides, length is always positive. Why? Because we have taken ordered set. So this length is positive. It means approximation from above is always greater than or equal to approximation from below for every partition P of AB. Also, if we take n is equal to supremum of this function over interval AB, then we know that mi would be less than or equal to m. Why? Because mi is supremum over a smaller interval. If this is AB, this is our piece, capital Mi. Suppose this is xi minus 1 xi. To supremum mi would be less than or equal to m. And this implies capital Mi into length. If we again multiply by length, both sides, length is positive, so no need to bother about inequality sign. And if we add all these, so this side we get upper Darboux sum, and this side we obtain this. But here m is independent of I, so this is sum of length of all those subintervals corresponding to partition P. So this sum is B minus A, which can be checked easily because it is another ways it is telescopic sum. So this is less than or equal to capital M B minus A. It means upper Darboux sum is less than or equal to always this rough approximation. So what is this rough approximation? This rough approximation is supremum over AB is this height. So this is capital M, this height is, this is supremum into B minus A. So this area is capital M into B minus A. And according to this area is small m into B minus A. Capital M is supremum of F over interval AB, and small f is this area. So UFP is in between these two rough estimates of this area. So now it means if we take collection of all these approximations, P partition of AB then this U, this is subset of R, which is bounded above by this and which is bounded below by this number, which is independent of P. So it means we can talk about supremum as well as infimum of this set U by order completeness property of R. But as I have said that UFP is always greater than or equal to actual area. So our aim would be to decrease this UFP to get the actual area. It means we are interested in infimum of this set U. So this we call upper integral, or this UF is equal to infimum of UFP. So why we take infimum? Because we would like to decrease it. We would like to get the actual area, which is less than or equal to UFP. So we are interested in infimum of this. And similarly, if I take collection of lower Darboux sum, that is approximations from below, then we would like to increase it. Why? Because LFP is always less than or equal to actual area. This is supremum of LFP. This is over P. So this is called UF. Whenever UF is equal to LF, then that would be equal to actual age. That will give us actual age. So this is the idea of Darboux. But the beauty is this, that both the ideas, either by Riemann or by Darboux, both definitions are equivalent. So idea of Darboux and idea of Riemann, both are equivalent. Yeah. But if we observe these definitions, then we can see, then in definition of Darboux, we have used only boundedness of F, not continuity of F. It means to discuss this definition, it is sufficient to assume that F is bounded on AB, not necessarily continuous. It means in general, if we are not interested always in area, then these definitions are workable if we assume only boundedness on AB. This is the first remark which I would like to give. And second remark is, in the definition of Riemann, which I have written here, in the definition of Riemann, it is difficult to compute, to guess what is the actual value of R and what would be delta corresponding to given epsilon in most of the cases. Yeah. So now these two are the remark that these two definitions are equivalent, and it is sufficient to assume that F is bounded function only, that F is bounded on closed interval AB. So now let me focus on this question that how much discontinuity an integrable function can afford. Because initially we assumed that function is continuous, and now we are saying that the function is bounded only. That's enough to assume this. Okay, so now question is that how much discontinuity an integrable function can afford. In this direction, my result would be Lebesgue criteria of Riemann integrability. Riemann integrability. Riemann integrability. What is this criteria? This criteria says that a bounded function F on closed interval AB is said to be Riemann integrable. No, not said to be. Is Riemann integrable if and only if the measure of set of points of discontinuities is 0. I am denoting set of points of discontinuities of F by dpf. So I'm taking this advantage that I'm assuming that many of us are familiar with Lebesgue measure. So here this measure is in particular Lebesgue measure. So it means that measure of dpf, that is set of points of discontinuities, is same. Let's see, this Lebesgue criteria will give answer of this question, or already given answer of this question, that how much discontinuity an integrable function, integrable in the sense of Riemann, can afford. So let's see the consequences of these results, this Lebesgue criteria. First, every continuous function, all the time my interval will be closed and bounded. So I'm not writing again and again. So every continuous function is Riemann integrable. Why? Because DPF. Why DPF is empty in this case? Because function is continuous at every point of this interval. And we know that measure of empty set is 0. So this implies by Lebesgue criteria, function f is Riemann integrable, which is continuous. Let's come to the second question. Step function is Riemann integrable. Why step function is Riemann integrable? Because in case of step function, set of points of discontinuities is always finite. And we know that measure of finite set is equal to 0, and this implies f is Riemann integrable. Means if it is Riemann, if it has finite number of points of discontinuity, then there is no problem in Riemann integrability. So let me explain with the help of example also. Suppose my interval is 0 to 5, and my function is step function. It means this, 2, 3, 4. In this interval, its value is 4. And at x is equal to 5, its value is 5. So what are the points of discontinuities here? 1, 2, because left hand limit is 0 and right hand limit is 1. Similarly, 2, 3, 4. And these are only 4 points at which function is not integrable. Means, what is DPF? Yani ki set of points of discontinuities. 2, 1, 2, 3, 4, and it is a finite set, and its measure is 0, and this implies this function is integrable. It means it can afford finite number of points of discontinuity. So what is graph of this step function? 1, 2, 3, 4, and finally 5. In 0 to 1, it's 0, then this, then this, then this, and finally at 5, 2, then 3, and then 4, and at 5, its value is 5. Its value is 5. So this is our step one. Now, the third consequence, every monotonic function is Riemann integrable. This will give another information. Why? Because we know that every monotonic function, either increasing or decreasing on closed interval AB, has countable number at the most countable number of points of discontinuities. And not only this, we also know nature of these discontinuities, in which we are not interested right now. So it means at the most DPF is equal to countable. And again, we know that Lebesgue measure of countable set is equal to 0. So this implies what? Every monotonic function f is Riemann integrable by Lebesgue criteria of Riemann integrability. So is Riemann integrable. And we can see this with the help of example also. Suppose my interval is 0 to 1 and my function is 1 here, half, and in this interval its value is 1 by 3 and so on. So this is a decreasing function. Here points of discontinuities are half, 1 by 3, 1 by 4 and so on. It means what is DPF? Point set of points of discontinuities, half, 1 by 3, 1 by 4 and so on. And measure of countable set is 0. It means 0. So therefore this function phi is Riemann integrable over 0, 1. So it means function can afford a countable number of points of discontinuities also. But for that, it is not necessary that the function should be decreasing. For that, I can take another example. For example, this is my function is 1 by n when x is equal to 1 half 1 by 3. I'm sorry, I think I should write not like this. I should write like this. When x is equal to 1 by n and 0 otherwise. It means at 1, its value is 1. At half, its value is half. At 1 by 3, its value is 1 by 3. But when x not equal to 1 by n, it's not of this form, then it is 0. So here, set of points of this function is not a decreasing function. This function is not a decreasing function. But here, set of points of discontinuities is again countable, and measure of DPF is equal to 0 because it is countable, and hence again this function is Riemann integrable over 0, 1. So not necessarily monotonic, but the points are countable number of points of discontinuity. And finally, my question is, can this DPF is equal to uncountable set? For this, the very common example which we teach in the class, that is the Dirichlet function. What is Dirichlet function? Suppose I'm denoting by 5. So we know that I'm going to finish my my talk within 4 to 5 minutes. Do I have 4 to 5 minutes, Dr. Uday?
Yeah, sure.
Oh,
Please do
thank
it
you.
in your own pace. No problem.
Fine, thank you. So what is phi x? So here I'm defining it is 0 when x is rational and x is in the interval 0 to 1, and 1 when x is an irrational when x is in 1. So there are, so most of the time, what reason we give that here LFP is equal to 0 for every P, UFP is equal to 1 for every P, and it means UF is not equal to LF. Let me write F here, not 5. F. So this, it means by Darboux definition, this function is not integrable in the sense of Riemann. But if we want to show this by using Lebesgue criteria, so by Lebesgue criteria, our question would be, that is, f is not Riemann integrable over 0, 1. By Lebesgue criteria, my interest would be that what is DPF. So here, as we know that, one can refer Professor Kumre's handbook to get the solution of this DPF. The DPF is here 0, 1. That is, this function is not continuous even at a single point of an interval 0, 1. Or this can be shown or this can be checked by using sequential criteria of continuity at a point. So DPF is equal to 0, 1, and we know that measure of an interval, the big measure of an interval is length of that interval, which is 1. This is not equal to 0, and this implies by definition of by criteria, Lebesgue criteria, this function is not Riemann integrable over 0, 1. It means, can I say that if DPF is uncountable set, then function would not be Riemann integrable? Can I say this with the help of this example? I think answer is no. Why answer is no? Because there are sets. There are sets which are uncountable, but measure of that uncountable set is 0. Which are uncountable, but measure is 0. And one of the examples is Cantor set. Very beautifully constructed set. I'm denoting it by C or maybe by F, because most of the time we use C for cardinality of real line. So let me write by F. So Cantor set is uncountable. This set is uncountable, but Lebesgue measure of Cantor set is 0. It means we can think of an example in which DPF, यानी कि set of points of discontinuity of that function is F, and since measure of F is 0, since measure of capital F is 0 because it is Cantor set and it is uncountable but its measure is 0, so by Lebesgue criteria that function could be, there would be Riemann integrable. So can we think this kind of example? Again, answer is yes. What is that function? That function is, I can define like this. F of x is equal to 1. When x is a point of Cantor set, I'm writing here so that there should not be any confusion. And 0 when it is in its complement. So my claim is that set of points of discontinuities of this function is C. And if my claim is true, then we know that measure of this is equal to 0. And by Lebesgue criteria, this function is Riemann integrable. It means we can say that if function has uncountable number of points of discontinuities, it's possible, but its measure is 0, even then that function would be Riemann integrable. So now let me give one or two comments for this claim that DPF is not C, I have denoted by, F. So to check that DPF is equal to capital F, we need some topological tools. The first tool is that Cantor set is closed and interior of Cantor set is empty. This implies Cantor set is nowhere dense. And if we use this fact, then it can be easily shown, because this implies its complement is dense This implies its complement is dense in 0, 1, and by using sequential criteria, we can show that dtf is equal to f. And to show it is continuous at every point of f complement, we have to use this fact that f complement is open. And by using these facts, we can show that the set of points of discontinuities is f. And finally, finally, let me show some slides. So this is Riemann, German mathematician. This is Darboux, French mathematician. And this is Henri Lebesgue, 20th century mathematician, French mathematician. And these are the references. In the first reference, the Cantor set is defined and all the properties of the Cantor set are there. Second one is the Professor Kumresen's book. And third one is the Goldberg, Mathematics from the Birth of Number, which is very nice book for the history of mathematics. Next one is the Elementary Analysis by Ross. Then the Calculus book by Anton Bevin and Davis. And this is another book, Corinth and John, second last, Introduction to Calculus and Analysis. Very nicely explained all the basics. And the last is, but not least, the Bartle and Sherwood, Introduction to Real Analysis. And thank you so much for listening this talk patiently. Now,
Yeah. Thank you, Dr. Singh, for your nice and insightful lecture. So I would now request all the participants to put their queries if they have any. Yeah, so you can ask Dr. Singh if you have any queries regarding his lectures. Okay, if not, I think two queries are there from the live stream. So let me read these queries out. So both the questions are from someone, Mr. Satyam Singh. So his first question is there any method to calculate area under curve other than this method? So other than this method, probably he wants to mean that without using this Riemann's process.
Certainly, there are methods which we teach in numerical techniques, because most of the time, for example, uh, I want to compute area under the curve sine x upon x. Suppose, yeah, in the interval on the interval 1 to 2. Then certainly we know that the function is integrable, but the question is how to integrate that. Okay, how to integrate that? In such kind of cases, we use numerical techniques, trapezoidal method and other methods, which we teach at the undergrad level in numerical analysis. And there are higher methods also to approximate area under the curve, not necessarily by these classical or analytical methods given by Darboux and Riemann.
Yeah, so thank you. I hope Mr. Satyam Singh is also listening to. The second question is what he asked, that this Darboux's conditions of integrability and this Riemann's original definition, whether these two methods are equivalent.
Certainly, I said in my talk also that these two definitions are equivalent. One may refer Ross book, chapter number 32, I think, that is proof is given. One may refer Bartle's book, the proof is given over there that these two definitions are equivalent.
And he also wants to know that is there any advantage of any of these two methods if certain problem is given?
Yes, that's a very nice question. That, as I said, that sometimes it's difficult to deal with when we are interested in actual area basically or actual integral. Sometimes it is difficult to deal with the definition of Riemann, because in the definition of Riemann, initially we should know that what is value of R. Yeah. So what we do in the definition of Darboux, the advantage is that we approximate area from above as well as from below. And if from above and from below, if both are converging and converging to same value, then we can compute area easily. So this is my viewpoint that for Riemann definition, I think it's little bit tricky to compute integral or in particular area, but with the definition of Darboux, for most of the simple functions or basic functions, we can compute integral as well as in particular case area.
Yeah, so these are the only questions. So if there is none, so let us give a big hand to Dr. Monika Singh for her nice lecture.
Thank you so much. Thank you so much, Dr. Uday, and all the participants which have attended the lecture and listening lecture patiently. Thank you so much.
Yeah, so our program is over now. So let me close the meeting. Thank you for your patient listening and the lecture, of course, madam. Thank you.